Well, hey, if there's a product rule, if there's a product rule, then there must be a quotient rule. And so it's a weird one. All right, and again, we're not proving things right now. I'm hoping maybe later on we will. But here's the derivative of two functions that are divided. All right, what you end up with is the bottom. I always start with the bottom. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now you're like, why did that happen? Well, it ends up being a common denominator thing, and you end up with g of x squared on the bottom of one of the fractions. Anyway, so there's a pretty complicated proof, and it looks like we're not spending time on that. But and I've not seen this before, high and low. So it says low d high minus high d low over low low. All right, so not seen that before, not heard that one before, but I like it. All right, with low not equaling zero. So that's kind of cool. All right, and I wanted to show why you wouldn't just take the derivative of the top and the bottom. Here's a classic: sine x over x. You can see that the slope at zero is zero, right? But if you took the derivative of the top, and I gave you cosine x, and if you took the derivative of the bottom and got one, well, cosine zero is not zero. Cosine zero is one. So that's not the slope there. So that means that would be wrong. So that's not the way you do it. All right. Hopefully, we'll see that particular one real soon. Close, close. All right, but all right. So here we go. Let's practice this. All right. So the quotient rule says the derivative of two things divided, and we could actually divide that out and then take the derivative if we wanted to. But this time we'll just follow the rule. So here we go. It is the bottom. And so I always say, well, the reason it's a fraction is because it has a denominator. So it always starts with the denominator. All right, and then the derivative with respect to x of the top, the numerator, okay, and fractions tend to have subtraction in them. So it's minus the numerator and the derivative of the bottom. And I think I got just enough room, x minus 5. Okay. And all of that divided by the denominator squared. Okay. So, all right. So here we go. Let's do this. So up top, I've got x minus 5. The derivative of the numerator is 6x squared plus 8x minus, be careful with this subtraction, 2x cubed plus 4x squared minus 7. And the derivative of the denominator is just 1. We got lucky there. All right. And then all over bottom squared. Okay. So we need to clean up the numerator a little bit. So let's do that. So let's let me look and see if Jean actually does that. Yeah, she does. Okay, so we need to do that too. All right, so heading back over here, pen. All right, so I'm going to multiply. I'm going to do FOIL on that right there. That'll be fine. So I'll have 6x cubed first, outside 8x squared, inside negative 30x squared. I could have gone ahead and combined those two, and then last. So last is negative 40x. Felt like I'd missed something, but I don't think I did. And then subtracting all three of those. Okay. All over bottom squared. Okay, so then let's finish it out. Combining like terms, I have 6 minus 2, so I have 4x cubed up top. So 4x cubed up top. And then squareds. 8 minus 30 is negative 22. Negative 22 minus 4 is negative 26. So negative 26x squares. Again, hopefully I haven't messed up anywhere. I feel pretty good about it. And then x's, I just have the negative 40x. There's not another one of those. And then plus 7. And all of that divided by x minus 5 squared. Okay, cool. All right, that's all for that one. All right, now on B, which is also, again, G. So G prime of x is equal to the bottom, x squared plus 1, times the derivative of the top. Minus, it's always minus on these quotients, minus the top times the derivative of the bottom. Boop. Okay, derivative with respect to x of the bottom, x squared plus 1. All divided by the bottom squared. It's interesting to me that she's not showing the proof, and the proof is very involved. And I guess that's the reason why. It's the quotient rule one is, and what it you end up doing is you end up rewriting this with and adding and subtracting a like term in the middle. And what happens is you get some factoring and stuff like that. And then when you take the limit and do the limit definition, everything just kind of falls into place. It's really cool. Okay, but anyway, so now if you were starting the problem fresh, I probably would start it this way with the second line. So x squared plus 1 times the derivative of e to the x. Well, the derivative of e to the x is e to the x. We haven't proven that, but it is. And then the top is e to the x, and then the derivative of the bottom is just 2x. Remember, the derivative of any constant is 0, okay? And that's going to be all over x squared plus 1 squared. Okay, and so now cleaning up the numerator, we definitely want to do that. We'll have an e to the x squared plus an e to the x, distributing right there, minus 2x e to the x. Man, there's not any like terms at all. No like terms at all. This is going to be the final answer. Over x squared plus 1 squared. And no sense squaring that out, just kind of leave it. It's best to have that denominator in that form. You do not, there's never going to be a time really where we're going to want to square that denominator. Just go ahead and leave it like that. And then your hopes may be that the numerator would factor a little bit, maybe cancel some of that out. But that wouldn't happen in here, man. Well, I mean, everything does have an e to the x. I mean, we could factor out. So another possible answer for that would be e to the x and then x squared plus 1. That's still not an x squared plus 1 by itself because I also have a negative 2x. So, that's interesting because that will factor, but it's not going to help us much. X squared plus 1 squared. Yeah, I'm going too deep down the rabbit hole here because, that factors as x minus 1 squared, but that doesn't help us because none of that's going to simplify. So there we go. All right, now I'm going to stop it on that. And so we'll call this example 2 A and B.